Hello everyone. So last time we left off with basically our tiling, and this time I promised that we're going to do the matrices. So what are the matrices? Well, you should already know what are the matrices, but we're mostly going to work with 4x4 matrix, and you're going to see why. But we're going to use matrices to represent transformations, right? Transformations being rotations of our object, translations, in other words, movement of our objects or scaling of our objects. And we do that by multiplying matrix times a vector. And which vector? Well, the vector we already have, right? And is exactly this vector, this float 4. So how are we going to define matrix? So while I'm at since I'm already in shader, we can just define it here, and it's going to be pegged float 4 times 4 or something like that. Maybe it's float 4 times 4. And then here we're just going to say our transform. And I'm going to change it. Sorry about this. Layout was somehow changed on my computer. So here we're going to have buffer 3, and I'm just going to move this to 4. Right? So that's it regarding this, and then we're just going to multiply our final vector times that matrix. So in this video we're also going to touch upon this parameter of a vector. That's quite often the question that I get asked. What is it? What it represents? So let's just go. I'm just going to explain quickly. So here you will often see this x, y, z, and then 1 here, right? So, and then we're going to have our matrix, right? So maybe I should just do it here, and I'm just going to say T for transform matrix, and then we have this vector, right? So this one will often get manipulated by this transform matrix, and its value can be greater or equal to 1, or it can be 1. And why is that important? Well, it's important because in the graphics pipeline, this x, y, and z get divided by this value. I'm just going to use W for it. So it means our x is going to get divided by it, our y is going to get divided by it, and our z is going to get divided by it. So if I was to place here, for example, 2.0, and if I was to run it, I would get an error because I forgot to pass this matrix here. So this one needs to be 4, and let's just create our matrix here. So, well, let's create first the matrix, then I'm going to explain it. So I'm just going to create small math group, then I'm going to create a new file. It's going to be Swift file, and I'm just going to call it matrix. So our matrix, we're going to import cmd. So we're going to have class matrix, and it's just going to be some static functions which will return our simd 4x4. So first one is identity, and we're going to return simd float 4x4, and here we can just return simd float 4x4, and it has constructor, and then it takes 4 components of simd float, and here it's actually float, and I'm just going to say 0, 0, 0. So hopefully you know what the identity matrix is. If not, I'm going to explain it as well in a second. I'm just going to define it so that I can explain first the shader stuff. All right, and then in our only render pipeline, we're just going to create that matrix. So here we're going to have private var transform is matrix.identity. That's fine. Transform buffer is of type constant buffer. Constant buffer of simd float 4x4, right? So And then we can create as usual getters and setters. 4x4 get transform. You already know the drill. We're going to set it and write that value to a buffer. So our transform is new value, and then transform buffer, right? Paste the data, which is transform. Right, that's it. And here we're just going to create a buffer and then paste it as well. Constant buffer, if I manage to type. Actually, we should set the value here so that it's written in a buffer, but I'm just going to say identity. And then here it's going to be transform buffer, and it's at position 3. All right, so now it should build, or not, because I just forgot something here. Hierarchical. All right, it works. So our image is smaller now, and why is that? Let's see our shader. Because right here I set this to 2, right? And if you remember previously, let's just run it once again. If you remember previously, let's get rid of this. Our position was, it was something like this, right? And this position was at 0.5 negative and 0.5 in y. And we divided by 2, right? Because our last component of x, y, z was 2. So this got divided by 2, this got divided by 2, therefore it's 2.25. If I was to set this last value to 0.5, this 0.5 would get divided by 0.5, and what's that? Well, it actually it is 1, right? Because it's same, it's kind of -1, so it will end up somewhere over here, and similarly this corner will end up somewhere over here. So all right, let's do this. Let's just play 0.5. And as you can see, it's filled. So that's what that parameter does. If I place it to 1, it's going to be original. And why is that important? Well, it's not super important for now, but it will be important in the future once we do projection matrix, because this last component of a vector will get manipulated, and that's how you kind of do this projection, right, into 3D. That's one use for it. And the other use is when we do translations, right? And so we're going to get to that. But first, let's just explain this identity matrix. So hopefully you did some linear algebra and you can recognize what identity matrix is, but it's essentially, it's just a matrix, right? Whenever you multiply identity matrix times some vector, right, you're going to get that vector, or if you multiply identity matrix times some other matrix, you're going to get that matrix, right? So basically it's like multiplying by 1. Then let's do our scale matrix. So here we're going to have x, y float, and z as a float, and similarly we're just going to return our matrix. But instead of it being identity, we're just going to say x here, y here, and z here, and this last component will remain the same, right? So you could get away with matrices when you're thinking about vectors, right? And the matrices, you could scale vector by 3 by 3 matrix, so you don't need to have 4 by 4. But you're going to see later why we need 4 by 4. But for now, we can just confirm that it works, and you can check the math. Just give me a second. Here, probably. And let's say that we have some vector 1, 1, 1, 1. Or 1, 2, 1, for example, and then we have our scale matrix here. So I mentioned let's scale x by 2, and then we're just going to have 0. So let's scale y by 2 as well. then we're going to have zeros, and let's just leave z as it is. When I multiply it, and somewhere here I have a bug or something. Error x at end of it. Aha, here, my bad. All right, let's try it. 1 here as well, right? Oh, this is weird. Ah, it doesn't need to have commas, my bad. All right. When I do a times b, right, matrix A, which is just a vector, x, y, and z, and then we have scale matrix, so x gets multiplied by 2, we get a 2, 2 is multiplied by 2 as well, so we get 4 for y, and then z is not changed because it's 1, 1, right? So you kind of already know how matrix multiplication works, right? If you have a row here, it gets multiplied by columns, right? So 1 gets multiplied by 2, 2 gets multiplied by 0, therefore it's 0, and 1 gets multiplied also by 0, therefore it's 0. Then the second row, right? 1 is here, 2 is multiplied by this middle, and etc. All right, so for the scale matrix, you can totally do it just by 3 by 3 matrix, but now for translations you cannot do that. So for translations, let's do translate matrix. So translate or move matrix. Translate. So it's going to be similar, but instead of doing it here, these are just set to 1. So this is like an identity matrix, but the actual translation part is done in the last row or column, depending on column, row. Is it row major? Is it column major? So if you're working with direct text, then it would be in last column, for example. But anyway, let's go to here. So for translations, we need this, right? So we're just going to set it to 0, 0, 0, 1, and here we have identity, right? And we have 1 to 1. And you can see already error, and that's why we need vector of 4 components, right? Because we cannot multiply vector 3 components times 4 by 4 matrix. And we need 4 by 4 because our translations are actually here. So let's just say 2, 2, and 0. We're not going to move z. So if I was to just give one last component here, we're going to get our vector, right? And so this is important. We had 1, but we decided to move it by 2 units, right? Therefore 3, right? 1 plus these 2 units is 3. There we had this 2, right? We moved 2 units in the y direction, therefore 4. And it kind of works out because, right, as you can see here, 1 gets multiplied by 1. Maybe I should just remove it quickly. So this 1 gets multiplied by this one. This 2 gets multiplied by this 0, therefore 0. This 1 gets multiplied by 0, therefore 0. And this 1 gets multiplied by 2. And this is why it is important to have this 1 at the end. So sorry, that's why we have this 1, right? So that we can multiply by this last row or column, depending on your order, right? But that's why it's important to have this one. And that's why you're going to see it often. It's called homogeneous coordinate. It's just so that we can do translation. One property, the other property is we can use it for projection as well. And that covers translation. So we can test scale and translation now. So let's just go to our coordinator. And here I'm going to say, so let's first test our scale. Transform is, my bad, matrix scale, and we're just going to scale it to cover entire screen. So we don't need a z component here. So if we multiply by 2, we should cover entire screen, and we do, right? Because we get for the coordinates, right? This goes to -1, this goes to 1, -1, 1. We previously had 0.5, and anyway, you figure it out. If we do translate, so we're just going to move 2 units up and to the right. We might not even see image. because it's out of the screen. But if we move 1 unit and let's just say 0.5 units up, we're going to get this, right? So our center was here and we moved our center. So let's say this is 1 unit, this is 2 units, we moved it somewhere over here, but we also moved just a half unit to the up. So our center got somewhere here, and therefore this top corner is touching the top, right? Because our center is not here. Anyway, you get the idea. You can play with those values. So further, last thing that we need to cover is actually rotation matrix, and I already had this. So hopefully you remember rotations from the high school or even primary school. But I'm just going to code this rotation. I don't want to go too much into the trigonometry. It's kind of weird to explain, but basically you can see already rotation x, rotation y, and we're just going to cover rotation around z-axis, right? The z-axis is one that goes towards our screen. So let's do that in our matrix. I'm just going to shamelessly copy paste this. I'm going to say rotation z on z-axis, and now we're not going to have this, we're going to have angle. It's a type float. And what were the values? So we had cosine of angle and then negative sine of angle. So we can just say here cosine of angle. We can say negative sine of angle. And I believe this is then sine of angle. And this is cosine of angle. And here we're just going to have 1, 0, 0, 0. Z must be 1 here, right? And this is 1 as usual. So let's just check if our rotation now works. Rotation Z, and we can rotate by some value, like 0.25, doesn't matter. And it's rotated, but it's kind of skewed, and that's because of the aspect ratio. So in order to fix that, we would have to work with projection matrices, but we're not going to do that for now. What we're going to do instead is just have 1 by 1 width and height. And if we go to constants, I can change this to 720. So that's for now. Later we're going to fix that, but now at least it's not skewed, so this is correct. And then in our coordinator, I'm just going to quickly do bar angle is of type float 0. And here, instead of setting it here, I can just set it somewhere over here and say our angle plus equal 0.01, and then paste it here, right? And we should now have animation, sort of. And yeah, we do have that animation. All right, that's it for this video. Hopefully you enjoyed it. Hopefully it's clear. And yeah, I get this question a lot. Why do we have that 1 at the end? And this is the reason why. Well, first of all, in our pipeline, x, y, and z get divided by value there. So that value is going to be changed with the projection matrices. But it's also important for translation part of transformations, right? Because to represent translation, we need 4 by 4 matrix. And that's why it's important. We just have 1 at the end, so that this bottom values, right? We had our matrix, so here we had 0, 0, and then x. So that 1 gets multiplied in the end by this x, and then it changes the x value. And then it's similar to y, right? Y here is multiplied, is added, right, to y here. Anyway, I'm rambling. That's it for this video. Please do play with this matrix calculator, because if it's not clear to you, you can just play with it. You don't have to do like matrix calculation by hand, because it's quite annoying. And yeah, best of luck. And if you enjoyed this video, please like, subscribe, and until next time.